All right, our lesson today is about graphing, and we're going to learn how to graph the square root function and some transformations of it. Yesterday we talked about inverse functions, and the square root function is the inverse of squaring function, but we know it better as a parabola, so we're super good at graphing these parabolas. All we're going to do now, I told you yesterday that inverses are a reflection across that line, y equals x. So it winds up looking like this, and we'll see more why it winds up looking like this later. But yesterday when we were doing our inverse functions, remember when we had to take a square root of both sides? We had to do the plus or minus. And then we said it couldn't be a function, again, because it's not passing that vertical line test. So to fix that, we're going to ditch the bottom part. And in order to ditch the bottom part, we're just going to graph only, now that it's a function, if we ditch the negative part, we're just graphing the positive square root of x. And that's how we take care of that, so that I can call this the square root function. We're only going to be talking about the positive value square root. So we're just going to start out by, this is going to be a parent function sort of thing. So this is the graph that you'll need to be able to do like really fast off the bat. The smartest way to do this is to pick numbers that have nice square roots. And so I know I can do the square root of each of those. Square root of 0, square root of 1, square root of 4, square root of 9. I didn't choose any negative numbers because I can't do the square root of a negative number and get a graphable point, which kind of already tells me that my domain, I can only pick x values that are greater than or equal to 0, and we'll see how that shows up on the graph too. So let's graph those ordered pairs. We've got 0, 0, 1, 1, 4, 2, 9, 3, and so on. So that's going to keep climbing. It doesn't climb very fast, but it keeps climbing forever and ever. So when I look at that, do you see how the graph only shows up for x values that are greater than 0? It's only showing up basically in this first quadrant, right? Because that's where the x values are greater than 0. On top of that, it's only showing up in the first quadrant. Like I said, this keeps climbing. So for the y values, all of our y values over here are also positive. You're going to be able to take the square root of something and get every possible y value as long as that y value is greater than or equal to 0. So that's kind of our basic parent function, the one that we're going to have to be able to graph at the drop of a hat. And the rest of these are just based off that, so we're going to slide it around, we're going to stretch it out. So here's a translated one. And we used to do like the vertex of our parabolas. I wouldn't call this a vertex this time, but there's still like an h and a k. And can you see how remember we have to do the opposite for the h, so your hk is going to be -2, -5 on this one. And that just means that instead of starting at 0, 0 like our parent function, we're going to start at -2, -5. And then it's going to have the same shape. It's just going to start at a different, I guess you could call this the new origin. The way that we're going to play this is we're going to always just make our table of some nice perfect squares, because I want to be able to square root them. And we used to do this where these technically aren't points on our graph, but if you count from your starting point, like this point right here, means that from that starting point I'm going to go over 1, up 1. From my starting point I'm going to go over 4, up 2. From my starting point over 9, up 3. So it's that same parent function, only it's just kind of slid to the left by 2 and down by 5, but all those same sort of points still work. If you don't like this parent function type of graph, go ahead and plug in convenient numbers into here, but I'm going to be doing all of mine this way, where we're just kind of starting from what we call the new origin. Now I also taught you how to find the domain of square root things. Remember that the stuff under the square root, the radicand, has to stay positive, or it could be 0. So that leads me to believe that that would be the domain of this function. And if you look at this function, doesn't it kind of start happening at -2? And we've got something going on for all the values bigger than -2. So that's my domain. And then we're just going to kind of think opposite of that for range. So the lowest this ever goes is down to -5. And it grows, it keeps growing, not very fast, but it'll keep growing forever. So it'll keep growing, starting down at -5 and going up. You see that those have to do a lot with the HK value on this one. We'll see if that always works. So this next one, see if you can do your HK. I'd go with 1, -3. So we're going to start our sort of, to me it looks like a sideways parabola, but only the top half. So that's where we're going to start our numbers. Here's how I'm going to make the table. I'm going to do x and square root of x, because I'm really good at square rooting these numbers. Look how good I am. Now, the only difference on this one is it almost has like a different, I don't know if you'd call it a slope to it, but it's got that 2 right there. So my third column here, I'm just going to double those y values. So like 0 doubled, 1 doubled, 2 doubled, 3 times 2. And if you remember doing this for parabolas, we're not going to ignore that. And these are the points, the xy points, that we can graph, assuming we're starting at this HK, this sort of new origin. So I'm going to go 0, 0. That's right here. 1, 2 is right here. Starting from that HK, we're going to go over 4, up 4. Over 9, up 6. So it's got the same shape, but can you see that it's kind of stretched out vertically? It's actually doubled vertically. It's got a vertical stretch of 2. The domain. Let's talk domain. Again, I like to look at it as the width if I'm looking at the picture. And it looks like the width of this graph is anything from x equals 1 and bigger. Another way you could figure that out is check the stuff under the square root. The radicand has to be greater than or equal to 0. X has to be greater than or equal to 1. So you can do it algebraically, you can do it off your graph, as long as you graphed it right. And then let's think y values for range. The lowest it ever goes is down to -3. It'll keep growing a little more rapidly than this other function because it had the 2 on there, but it'll be going up forever, starting at -2. Did I write a -3? Sorry guys, starting at -3. The only reason I caught that is because I was trying to compare this to my HK again. It kind of seems like that HK is pretty reliable on corresponding with the domain and range. A couple more just to make sure you got this. So come up with an HK for me. -7, 2. I'm going to make my standard, they call this the parent function table. I'm taking the square root of each number. Now, like the slope or the weirdo thing going on here is this negative sign out in front. So I'm going to want to find out what happens when I negate my y value, when I negate my square root. So -0, still 0, -1, -2, and -3. So this is actually what I'm interested in. This parent function was helpful, don't need it anymore. So now from my origin, I'm going to go 0 and 0. I'm going to go over 1, down 1. So from that new origin, over 1, down 1. From the origin, over 4, down 2, over 9, down 3, And we actually get the bottom half because we had that negative sign in front. It reflected it. It kind of kept the same sort of x values going, but it reflected it. Let's think about our domain. So again, if you want to do it the algebra way, x should be greater than or equal to -7. If we check the graph, that seems legit because it starts back at -7 and continues that way. The thing that's kind of different about this one is the highest the y value goes is 2, but then it opens down. So this range is actually a little different than before. Still, we're using those HK numbers, but since it was reflected, it's going to be less than or equal to 2 is our possible x values. And just one more. I thought the HK might be confusing on this one. That's why I decided to do it. Plus it has a fraction. I don't know. Let's try it. HK. -5, comma, nothing, right? There's nothing there. So -5, comma 0 is my HK. -5, 0. And so that's kind of my starting point. We'll get really good at that, taking some nice square roots. And this time, I don't know, I probably shouldn't call it my slope, but my A value is probably what they call it in the book. I'm going to half each of those original square root values. So half of 0, half of 1, half of 2, and half of 3. I can ignore that parent function because I got my use out of it. And now from this -5, 0, I'm going to go over 0, up 0, over 1, up just a half, over 4, up 1, and over 9, up 1.5. So that's actually kind of squatty. It's not quite as tall. I don't know. They call that a vertical shrink. It kind of just smashed it down a little bit. Doesn't really affect the domain and range though, right? It's still infinitely going to the right. It's growing super slow this time. I don't know if you believe me, but if you take the square root of 100 million, it's still going to be pretty big. So this is going to slowly keep growing and growing. Could also do it the algebra way, but can you see that -5 and bigger is the width of the graph? And the height of the graph is anything above the x-axis. So the lowest the y value gets is 0. Do you believe me that it's going to keep growing? Trust me, I know what I'm doing. It should keep growing, although very gradually, so the range is y is greater than or equal to 0. I hope this goes okay for you. Tomorrow we're going to do the same thing, only we're going to see what the cube root function looks like. So it's not going to look like a parabola. Maybe you can think of what that might look like.